NanoHub U, online instruction.
So welcome back to our discussion on the Landauer approach to carrier transport. So we're trying in these two lectures just to get comfortable with this way of treating electron transport in small devices. In last lecture, I derived the expression. We looked at it a little bit about the various terms, transmission, number of channels. In this unit, we want to get a little more familiar and actually do some calculations. And then we'll be ready to apply this approach to the ballistic MOSFET in the next lecture. Okay, so I'll just remind you, this is our nano device, our generic nano device. A couple of things to remember is we have these very special contacts that I've called Landauer contacts. They're large, they're maintained near thermodynamic equilibrium by frequent inelastic scattering that mixes all the energies and the momentums up. And consequently, they're each described by a Fermi function. The Fermi levels may be different because we may apply a voltage to the second contact and lower its Fermi level with respect to the first contact. Current will flow, and you know when current flows, you're out of equilibrium, but we're assuming that these contacts are so large that the perturbation away from equilibrium is small enough to be neglected, and we can describe our contacts with Fermi functions. We're also making the very important assumption that we have independent energy channels. Electrons flow from contact 1 to contact 2 without changing their energy. Once they get into the contact, the inelastic scattering mixes everything up and changes energies and restores the thermodynamic equilibrium in the Fermi function. But the device itself has no inelastic scattering. Okay, now these are the results that we derived. We derived this expression for the current, and we want to work more with this in this lecture and get more familiar with this. We also derived an expression for the electron density within the device. And again, we're not trying to resolve anything spatially within the device. To do that properly, we would need to do something like a Boltzmann equation. We're just thinking of this device as a small, uniform device. The electron density is uniform within that device, and we have a way to calculate it in terms of the density of states and in terms of the Fermi functions of the two contacts. Okay, so let's look at the current expression in a little more detail, and in particular, let's look at this term F1 minus F2. So you can see that when the Fermi functions of the two contacts are the same, no current will flow. Current only flows when F1 is different than F2 over some energy range. And the range over which that's true is what we call the Fermi energy. That's what we focus on when we want to understand current flow. Those are the range of energies that are important. So we can get a picture of that from these diagrams. This is at 0 Kelvin. At 0 Kelvin, there's a probability 1 that all of the states below the Fermi level are filled, and then a probability 0 that the states above the Fermi level are filled. If we have some finite temperature, then the transition from 1 to 0 occurs over a range of a few kT, just not as sharp. Now, if these are the Fermi functions of contact 1 at 0 K and at room temperature, say, then perhaps at contact 2, I have applied a positive voltage and lowered the Fermi energy. Well, if I'm at 0 K, I'll just pull the Fermi energy down at contact 2. And then I'll have a range of energies over which F1 is bigger than F2. And that's the range of energies over which current will flow. I would call that the Fermi window. Now, at room temperature, if I pull the Fermi level of contact 2 down with respect to contact 1, I'll just pull everything down. The transition is not an abrupt one, but there is still this region of a width depending on the bias that I've applied and the temperature which smears out the transition. I'll call that the Fermi window as well. So that's what the Fermi window looks like when there's a fairly large bias on contact 2. If there's a small bias on contact 2, I just pull the Fermi energy in contact 2 down a little bit, and the Fermi window begins to look like a delta function at the Fermi level. If I do the same at room temperature, I'll just pull the Fermi level down a little bit. There'll just be a small energy range now, and now it'll depend on the temperature or the width of that energy range. That also begins to look a little bit like a delta function, and we'll call that the Fermi window as well. So this range over which F1 does not equal F2 is called the Fermi window. Now let's look at this a little more carefully in the case that which we apply a small bias. This is like the linear regime of a MOSFET. If it's a just a two-contact conductor, we would call this the regime of linear response. So here's our general expression. We're going to focus on F1 minus F2 and see what it looks like when both contacts are at the same temperature. That's an assumption we're making here throughout all of this unit, all of this course, in fact. But we're going to assume that we apply a small voltage to contact 2. So here's the Fermi function of contact 1. I can write the Fermi function contact 2 by saying it's going to be close to the Fermi function of contact 1 because we've just applied a small voltage to contact 2. So I can write F2 as a Taylor series expansion of F1. It's F1 plus dF1 with respect to the Fermi level plus delta Fermi level, because all I've done is to change the Fermi level in contact 2 a little bit. So I'll write that Taylor series expansion. Now if you look at this Fermi function, you can see that if I take a derivative with respect to the Fermi energy, I get the same answer except for the sign as if I take a derivative with respect to the energy. So the derivative with respect to EF is the same as a derivative with respect to E, except for the minus sign. So this is the way we usually like to write it, so I'll write it that way. Okay, now I can say that, well, the change in Fermi energy, this occurred in I changed the Fermi energy in contact 2 because I applied a small voltage. A small positive voltage lowers the Fermi energy, so the change is minus Q times the voltage that I applied. Okay, now all I have to do is subtract F1 minus F2, and I'll find what this quantity looks like when I have a small bias applied. And what I get is it's just related to this quantity dF1 dE, just a derivative of an equilibrium Fermi function, something that I can take, and it's proportional to the voltage, Q times the voltage. Okay, now if I take this and put it into this, and evaluate the expression, what I'm going to find is I get a current that is proportional to voltage. That's why we call this the regime of linear response. The constants out front would be the conductance, and the conductance would be given by this expression. I've simply used this Taylor series expansion for F1 minus F2. The expression I get is for the conductance is given here. So that's a very important expression that is widely used in many different cases, not just for small MOSFETs. Okay. So we have now determined that this Fermi window here that we sketched a few slides ago is actually minus the derivative of the equilibrium Fermi function with respect to energy. So we know what it is. So this is what we call the window function. So the window function is just this minus this derivative of the Fermi function. If you integrate that across all energies, you'll see that it integrates to 1. So when it's narrow, and the width is a few kT, so when it's narrow and it has an area of 1, it's going to look like a delta function. And in some cases, it will be convenient to treat it as a delta function. Now, this brings us to a topic we can discuss, something that you may have heard before, the quantum of conductance. So let me look at 0 Kelvin. At 0 Kelvin, this Fermi window is very sharp. kT is very small. So minus the derivative of F naught with respect to energy can be considered a delta function at the Fermi energy. That makes this integral easy to do. So we find that the conductance at 0 Kelvin is just 2 Q squared over H times transmission at the Fermi energy times the number of channels at the Fermi energy. We get a very simple expression for the conductance at low temperatures. Now there's something important here that I want to point out. in deriving the expression for the number of channels at the energy E, which we did in the last lecture, we assumed a 2D density of states. Remember, the number of channels, we need a velocity, so that was the x-directed velocity at that energy, but we need a state, and that brought in the two-dimensional density of states. But the expression that I use for a two-dimensional density of states is one that is derived for a large two-dimensional area. In small structures, the density of states can be modified by quantum confinement, and we can start to get discrete and countable numbers of states. So for the large structures, and we're going to primarily be thinking about large structures. In a large structure, the width of the resistor, say the width of the MOSFET, we're going to find, our expression tells us that the number of channels just scales with the width of the resistor. But in small structures for which we get quantum confinement, we can't use this density of states that comes from a large material. We have to compute the density of states properly, assuming boundary conditions on the wave functions. This is where the term modes comes in for channels. The number of channels comes in discrete countable units in a nanostructure. So that's an area that is fascinating. There's a lot of work in nanoscience and nanotechnology in that area. And it's something that is by now a well-established experimental fact. For example, these are some experiments that were done in the late 1980s with very small two-dimensional resistors with a very short channel such that the transmission across those channels was near ballistic when the measurements were done at low temperatures. The width of the channel could be electrically varied by reverse biasing Schottky barriers. And this is the measured conductance versus that width. So in a large structure, our expression for the number of channels, we would just say that the wider the structure is, the higher the conductance is, the conductance should be proportional to W. What you find, however, is that the conductance goes up in discrete steps. And we can, so this is an example of quantized conductance. We're seeing the number of channels increase discretely as the number of states that can fit into that width and make the wave function go to zero at the two edges of the resistor. As that increases, we get discrete numbers of modes or channels. So that's an example of quantized conductance. As I said, we're going to be working with MOSFETs in which the width is wide enough that we don't see this quantization, but the general expression that we work with handles both cases. All right, let's look a little more carefully at the conductance for T is greater than 0. Then the mathematics can get a little more involved. I don't want to work this out too much here now, but if we take our expression, if I divide by this integral and multiply by this integral, and I define a quantity, m in brackets, as that integral that I divided and multiplied by, I'm going to interpret that integral as the number of channels in the Fermi window. Right? So that makes sense. There's my Fermi window. Here's my number of channels. If I do that integral, it's the number of channels in the Fermi window. If I define an appropriately average transmission across this range of energies, then you can see that I can write the conductance in a general way. There's this quantum of conductance, 2q squared over h, times an average transmission, average in the energies of interest that are within the Fermi window, times the number of channels in the Fermi window. So it's just a convenient way to write that expression. In order to get numerical answers, I've got to do all of these integrals. At 0 Kelvin, things simplified. It's the quantum of conductance times the transmission at the Fermi energy times the number of channels at the Fermi energy. And this is the expression that's used to interpret those experimental results we saw a few slides earlier. Now, let's look a little more carefully now at the ballistic case and look at the conductance, when the temperature is greater than 0, because we're primarily interested in MOSFETs at room temperature. So this is our general expression for the conductance. This is our expression for the number of channels as a function of energy. And we're assuming wide structures where the discrete nature of the channels won't be an important factor for us, so it's just proportional to W. We're assuming ballistic transport, so the transmission is 1. And we know the Fermi function, so we can work out this derivative. So if you do that, we'll get an expression like this. I'll rewrite the minus df naught dE as a plus d dEf, which then I can bring outside the integral. Then I can do the integral. Then I can take the derivative. There's a little bit of work to do that. I don't want to go through that. It's done in the lecture notes. I'll simply quote the result. This is the result of that integration. So this brings up another Fermi-Dirac integral, this time an integral of order minus 1/2. Now we can simplify that for non-degenerate statistics, and that makes life easier. For non-degenerate statistics, Fermi-Dirac integrals always reduce to exponentials. So we simply replace the Fermi-Dirac integral with an exponential. Okay. Now, if I look at my expression for the electron density, we also worked out in the last lecture an expression for the electron density. It involved Fermi-Dirac integrals of order 0. They reduce to exponentials. So I can write the electron density as the 2D density of states, effective density of states, times an e to the eta f. And remember, eta f measures the location of the Fermi energy with respect to the bottom of the conduction band in units of kT. So you can see I can relate the electron density to e to the eta f, and I can use that in the first equation. Then along with the definitions of the 2D effective densities of states, I can put that all together, and I can rewrite this ballistic conductance in this form. So I've simply eliminated the e to the eta f. We've used the definition of the effective densities of states. This quantity v sub t was a collection of constants that came out of this algebra, and it's a collection that has units of velocity. This is the unidirectional thermal velocity, and we've seen it before when we were doing the ballistic treatment in the lecture 1 of this unit, and we'll discuss it a little more in this unit. It will come back again and again. It's an important velocity in our thinking about ballistic MOSFETs. So if we would like to now, we could divide by L, and we could multiply by L. And when I do it that way, you can see that we're achieving this quantity that has the units of mobility. This is the ballistic mobility we saw earlier in lecture 1. So the bottom line of all of this is that if we take our general formula for the conductance in the linear regime, if we evaluate it in the ballistic limit when t is equal to 1, we can write the result in the traditional textbook way that the diffusive conductance is written. NQ mobility times width divided by length. We can write it in the same form as long as we define this thing we call the ballistic mobility. So that ballistic mobility is something that's going to come up in our discussions as we talk about ballistic MOSFETs and quasi-ballistic MOSFETs. Okay, there's one more thing I'd like to do in this lecture, and that's to consider the case of a large bias. This would be like the on-current of a MOSFET. So we have these two Fermi functions. If we apply a large voltage, we lower the Fermi energy in contact 2, and that means F1 is much bigger than F2. We can ignore F2, and our current simply is given by this integral. We just ignore F2. Well, again, that's an integral that we can do. We're considering the ballistic case, so the transmission is 1. We know the number of channels. We know the Fermi function of contact 1. We put it all together. We do the integral. We can do the integral. If you work that integral out, again, you're going to get Fermi-Dirac integrals, this time an integral of order f plus 1/2. If we work on this a little bit, use our definition of the thermal velocity, the unidirectional thermal velocity, our definition of the effective density of states, we can do a little bit of algebra, and we can rewrite this on current as thermal velocity times effective density of states divided by 2 times this Fermi-Dirac integral of order 1/2. All right, so it's a little bit messy algebra, but no rocket science. We can go through and work that out. Let's look at it a little more carefully and see what we can make of this. this is the result we get from evaluating those integrals. In the non-degenerate limit, Fermi-Dirac integrals always reduce to exponentials. Again, we can look at our carrier density. It was related to Fermi-Dirac integrals. Eta F2 is very small because we've applied a large voltage to the drain and lowered the Fermi level in the drain, so we can ignore that. We can simplify this for non-degenerate cases, and then we can ignore the contribution from Eta F2. So we have a simple expression for the electron density as a function of Eta F. We can insert it in the first expression, and what we will find is that we can write the ballistic on current in a very simple way. And we're going to see this again when we do the MOSFET. It's charge, Q, times the sheet carrier density times velocity. And the velocity is the thermal velocity. So take some time to go through this algebra. Look at the lecture notes if you'd like to see how it's done. The final result is simple and easy to remember, and it's something that we'll see from time to time. All right, so that's it. Hopefully, by sitting down, going through some of this algebra, reviewing this lecture, you'll get comfortable with using these equations and applying them to different situations, and you'll be ready to consider the ballistic MOSFET in the next lecture. These are the takeaway messages. We've been working with the current expression in the ballistic limit where the transmission is 1. We considered the low bias case where F1 is about equal to F2. We saw that current is proportional to voltage. G sub B is the ballistic conductance. The ballistic conductance, if we choose to do so, we can write it, we can make it look like the traditional diffusive expression, which varies as W over L. But to do that, we have to define this thing called a ballistic mobility, whose physical significance we have not yet discussed, but we will. And we'll come back to that in a later lecture. Under high bias, F1 is greater than F2, and we can write something we would call the on current simply as charge times velocity. The velocity is the thermal velocity. So with that and the previous lecture, we're ready to apply these approaches to the ballistic MOSFET. We'll continue this discussion in the next lecture.